Morning, everyone. We're going to go ahead and get started here. Welcome to the Montana Generation and Transmission Working Group. My name is Ben Brower. I'm the supervisor of the Energy Planning and Renewables section in the Montana Energy Office. We're housed inside of the Air, Energy, and Mining Division at the Montana Department of Environmental Quality. Got a few housekeeping notes before we go ahead and get started. As you probably realized by now, those of you in attendee mode are in listen-only mode. If you go ahead and click your speaker view, you should be able to track the speakers that are currently presenting. A reminder to panelists to please mute and turn your videos off until your panel is in session. For those of you listening in who have questions, we're going to be handling questions via the Q&A window. You can click the Q&A box on your Zoom toolbar in order to submit questions. We'll be getting to questions at the end of each panel. When you go ahead and submit questions, just to personalize this a little bit, we'd encourage you to include your name and association, the group or organizations you're with, to let our panelists know who's asking the question. Please note that this webinar is being recorded and we plan to post it to DEQ's website on the page listed there. Quick preview of the agenda. We're going to kick things off with brief opening remarks from Chris Dorrington, the administrator of the Air, Energy, and Mining Division at DEQ. We've got two panels lined up today, one on green hydrogen, led by Dan Lloyd, the bureau chief of the Energy Office here. And then the second panel, led by my colleague Kyla Mackey, is going to be focused on innovation in energy delivery. We're going to wrap things up today with a spotlight on the Cabin Creek Solar Project, a Basin Electric and Clenera collaborative building a solar project in eastern Montana. And as I noted before, we'll go ahead and do Q&A at the end of each panel. So to kick things off, we've got Chris Dorrington lined up. Chris, you ready to roll? A little choppy there. Give it a whirl, Chris.
All right. If I lose it, I'm going to just hand it to Dan and do our intro. Welcome, everyone. Thanks for everyone joining us today. The focus for this Generation and Transition Working Group meeting is innovation, which is somewhat broader than usual. Countless topics could have covered under that umbrella, but we're focusing on three topics that are likely to increase in importance throughout Montana and the West in the coming years. The first is clean hydrogen, a resource on
You know what, Chris, we're having a hard time hearing you. We may go ahead and pass it over to Dan to provide our introductory remarks.
Great, thank you, Ben. Just building on what Chris said, that the theme of today's working group meeting is innovation. We typically have it narrowed in a little more tightly, but we think that innovation was a good umbrella topic with a lot of things that we could have been talking about, and Ben did a nice run through of the three panels we're going to have today. So I'll just say that as we continue navigating the energy transition that's happening in Montana and really around the world, it's important that we have these kinds of conversations to keep up the dialogue so we better understand what opportunities are out there and, frankly, what are the implications of these changes that are happening in our energy sector. So thanks to everybody for being here today. Special thanks to all of our speakers and to the Montana Energy Office for pulling this together. And with that, I will kick it off to myself to introduce the first panel. So our first panel, as mentioned, is going to be on green hydrogen. We've got two great speakers for you today. This is a topic that's really gaining interest and momentum in the West and really around the world. Our first speaker today is going to be Dr. Laura Nelson. She's a vice president at Stratogen and the executive director of the Green Hydrogen Coalition. And prior to this, Dr. Nelson served as the energy policy advisor to Governor Herbert of Utah from 2014 to 2020 and was the executive director of the Utah Office of Energy Development. I can speak from my own experience that Dr. Nelson is a true leader in the energy community in the West, and we're very excited to have her today. After Dr. Nelson, we'll be hearing from Michael Ducker, who is Vice President of Renewable Fuels in the Western region at Mitsubishi Power, a power generation and energy storage solutions provider in the energy industry. In this role, Michael oversees Mitsubishi's recently launched renewable fuels business focused on delivering carbon-free fuel solutions to the power industry and other verticals. Michael is also responsible for sales and business development for new power equipment within the Western region of the US. And I really could have gone on a heck of a lot longer on both of these panelists. They have quite impressive resumes, but I'm gonna leave as much time for them to speak to you today. And as Ben mentioned, we're gonna have time for questions, so please enter those into the Q&A as we go. And with that, I will turn it over to Dr. Laura Nelson.
Hey, good morning, Dan. Thank you so much for that very gracious introduction. It's really great to be with everyone today and to have the opportunity to speak with folks, stakeholders, constituents in Montana that are really engaged and interested in what's happening in the energy space. As you so eloquently stated, our energy system is under a significant transformation today, and how we continue to realize the benefits that we've so appreciated over the many decades of energy security, reliability, and affordability, and how we're going to propel that into the future, I think is top of mind for many of us. So pleased to be with you today to talk about green hydrogen, which is really a growing technology. I have here in my title that it's new. It's really not so new. We've known how to do this for a while, but what is new certainly is the momentum and the scale of where green hydrogen is today and what's planned next. So if you'll go ahead and progress to my next slide. So the Green Hydrogen Coalition, we really recognize that we have significant issues that we're facing today in terms of environmental considerations, and that really is driving in large part the energy transformation that we see, whether we're addressing policy goals and perspectives, social considerations, and certainly demand factors for clean energy. Climate change is top of mind, and certainly we want to provide a clean energy economy that works for everyone, and we believe that green hydrogen can be a game changer in helping us to meet our mutual goals of addressing climate change and providing that clean energy economy for everyone. So next slide, please. At the Green Hydrogen Coalition, our mission is very straightforward. We want to facilitate the policies and practices that will advance the production and use of green hydrogen in all sectors, where it will accelerate a carbon-free energy future. As a 501c3, our educational nonprofit, our approach is very unique as an organization. We build top-down leadership and momentum by focusing on large projects that can be deployed at scale and can simultaneously leverage multi-sector opportunities to realize supply and demand at scale. Next slide. And you're going to hear more about a project today, I believe, from Mike. But we at the Green Hydrogen Coalition really are able to do our work, continue to provide education and drive those policies and practices because of the generous donations that we receive from our many, many supporters who cover large energy developers, utilities, as well as engineering firms. So go ahead and move forward, please. And what we're up to really is transitioning a commodity market that already exists today and taking that commodity and using it in other scalable applications that can help, as I said, to drive that green, clean energy system that's going to promote affordability, reliability, and certainly resilience. And hydrogen is today a globally traded commodity. About 100 million tons are traded a year. The challenge is that most of that hydrogen that's traded today is in fact made from fossil resources, either natural gas or coal. There is some small amount of the production that also utilizes carbon capture and sequestration, but not a lot. And so with a very small percentage of this hydrogen produced today coming from green sources, it has a very large carbon footprint. The hydrogen production market today represents about the 6th largest emitter for CO2 globally. So the market itself is an important market in terms of the hydrogen commodity that's produced, but it also is very relevant in the sense that this is a market that can be transitioned to a green, clean hydrogen molecule that looks just the same as the gray molecules or brown molecules that are produced today. Brown often referring to hydrogen produced from coal, and gray referring to hydrogen produced from gas, to really transform significantly this globally traded commodity that is used in multiple sectors. Next slide, please. So for green hydrogen, you might say, well, what is it? What is green hydrogen? So we do have a definition of green hydrogen. Green hydrogen is hydrogen that is not produced from fossil fuel feedstock sources and also does not produce incremental carbon emissions during its production. Next slide, please. We at the Green Hydrogen Coalition are technology agnostic. So when we talk about green hydrogen, we want to create all the pathways for producing this molecule, which is really a zero carbon molecule, through the production process to its use. So you can use solar and wind or hydro, just as an example, which are renewable energy resources, as an electricity source or a power source that can go into a machine, I'll call it, that's called an electrolyzer. That electrolyzer takes water and splits the water into its relevant molecules of hydrogen and oxygen, and the hydrogen that's produced then is considered a green hydrogen. Similarly, you can use biomass and do biological processes and reforming, very, very similar to processes that are used today. And you can also use biogases or biomethane. So biological and thermal chemical pathways are also options for producing green hydrogen and can provide a source, in fact, for cleaning particular waste streams that might exist today in terms of collecting biomethanes. Next slide, please. So just like hydrogen today, just like this commodity that already exists and is globally traded, significant commodity, there are various applications for which we can use green hydrogen. We can use it in transportation. We can use it in the power sector. We can use it in industrial applications, chemical applications, and also in agriculture. So right now, hydrogen is used in many of these sectors. We're going to talk a little bit about today more in detail what's happening in the power sector, because this is a sector where the use of hydrogen is growing significantly. But we also have these other opportunities to displace carbon-based hydrogen with a non-carbon or green hydrogen. So potential to reduce emissions exist across many sectors. So next slide, please. So the other great thing about hydrogen, in addition to being applicable to these many sectors, is that green hydrogen actually can be used for storage. So you can produce a green hydrogen, let's say when the wind is blowing or the sun is shining, and then you can store it in various ways. We're going to talk about one particular way. I'll maybe highlight it, and I bet Mike will go into more detail, but you can then store the hydrogen in either rock formations or thermochemically or in other types of containments. And that green hydrogen can be stored and used later and released as a fuel source. And the nice thing about it is it can be stored for long periods of time and the fuel doesn't degrade. So we have batteries today, and at the Green Hydrogen Coalition, we're supportive of all types of storage. We think that batteries are terrific, but they really are a short-term, short-duration storage opportunity. There's also compressed air energy storage that can be used. Pumped hydro, of course, shows up as we start to move toward those longer duration energy storages. But if you want to really have long duration, significant energy storage, green hydrogen is something that can be used to store energy and really to help balance the system between when resources are available and when they're not, and the differences in demand that occur on a system as well. So next slide, please. So I mentioned that our approach is really to focus on projects that can demonstrate the scale of green hydrogen. So our first initiative is focused on the Intermountain Power Project, or IPP, which is a project that's located in Delta, Utah. And the goal here is to really leverage curtailment of low-cost, purpose-built wind and solar, or wind and solar, as we said, curtailed, that can be achieved from the grid. So either from the system that's curtailed or is purpose built, take that, use it to produce the green hydrogen, and ultimately displace natural gas in the production or the combustion process at the site. And we believe that through this process of this Intermountain Power Project, that we can in fact realize scaled green hydrogen use and also storage. So if you'll go ahead and move to the next slide. So I think Mike might go into a little bit more about the Intermountain Power Project, but just quickly, the Intermountain Power Project is a project that's in operation today. It's about an 1,800 megawatt coal facility that's going to be converted to a combined cycle gas turbine facility. And there is offtake already in place, predominantly in California, with the Los Angeles Department of Water and Power. So you have this large project supply, and then you have the offtake. But also co-located with this particular project is some large salt formations. These salt formations, or these salt domes, can actually be engineered to store hydrogen. So this project is particularly elegant in the fact that you have large-scale production, coal today being converted to gas-fired combustion turbine burning green hydrogen on day one of operation, which is not a decade from now, but less than 5 years from now. This project actually is planned to be online in the summer of 2025, with the production of green hydrogen going into the turbine, and hydrogen that isn't used immediately can be stored in these salt caverns. Very significant opportunity for realizing in the West, in fact, large storage potential that can be used as a fuel source across our power system and those other sectors I mentioned as well. So next slide, please. So there are many ways. We don't have to store the hydrogen, but it's a great way to have it available for use there at the site, and also available as needed across the system. But we can also transport hydrogen. It is transported today in various ways. For example, in Texas, where they today store large amounts of hydrogen in salt caverns, there are over 600 miles of pipelines to move and also to store. The pipelines can act as storage to move and store the hydrogen molecule. Hydrogen is also transported in tanks and canisters. There are different types of carriers that can move hydrogen, very similar to other chemical forms like methanol that we might transport. And importantly, in the situation of the IPP project, what we're doing is we're essentially taking power, we're converting it into a fuel like a gas, and then putting it back into the power sector. So it's kind of a power to gas to power solution. So we can then take those green molecules, if you will, and serve as a green energy source going back onto the grid using existing transmission and distribution systems that are already in place. And so again, another elegant piece of the IPP project, but another way that we can also move and transport green hydrogen is in fact through our power system. So next slide, please. So what's standing in the way today, really, of scaled green hydrogen is that the market is new. Today, green hydrogen is more expensive than the alternatives. You may be asking, well, if, gray and brown hydrogen are particular challenges, why aren't we producing a lot more green hydrogen? Well, the issue really is getting it the right market design so that we can drive scaled production of green hydrogen and utilization in all of the sectors where it can in fact realize decarbonization. So next slide, please. So at the Green Hydrogen Coalition, we really are focused on what does that market design look like as we undergo system-wide transformation. How can we engage in planning across all of these sectors and also promote valuing the benefits of green hydrogen and not just the cost? So next slide, please. So when we look at appropriate market design, what we're talking about is getting the design right so that you drive the capital, infrastructure, and investment, and you can progress impact and innovation. And you may wonder, okay, what does it mean to get market design right? Well, a couple of things. One is we want to understand where are the demand centers and how can we bring aggregated demand, because there is, as I mentioned, demand out there for green hydrogen, because that demand, when it's realized, is going to drive the capital investment and the production, and that's going to result in progress, impact, and innovation. And I think I'm super close to being done. I see Danny probably wants to hurry along here. So I'll go through my next couple of slides, Dan, and I'll wrap up. So really, cost is a factor today when we look at green hydrogen. It's the reason that we need to get to scale so that we can drive down those costs, but the benefits are really substantial for green hydrogen. I won't go through all of these, but one is we can avoid build out of our grid system that maybe we don't need today. Not that we're going to displace it all, but we can defer certain build out. And of course, we can also realize repurposing existing infrastructure, plus all of the other benefits, including jobs. So next slide, please. And we are really up to driving this across the West. So we have partnered with NASEO, National Association of Energy Officials, and the Western Interstate Energy Board to pull together states in the West, including 2 Canadian provinces, to talk about what are the best practices and approaches to driving green hydrogen production in the West, so that we can realize economic and environmental success for all of our communities across the West. And you can learn more about the Western Green Hydrogen Initiative at the website, westernghi.org. Next slide. I promise I'm almost done. This is what it looks like. This is a large part of the country where we can demonstrate coming together, partnering, and collaborating. We can realize key results by driving a clean energy solution that helps us to meet multiple goals and provide for multiple solutions. And we're going to focus on the Intermountain Power Project, how that's going to derive demand and supply opportunities, as well as infrastructure, the midstream approaches. We're also going to look at what's happening in Montana with green hydrogen production and how we might realize, for example, an I-15 infrastructure corridor for movement of green hydrogen. And again, our partners, NASEO, WEEB, and we also have generous sponsorship from Mitsubishi Power and SoCal Gas to kick off this initiative. Next slide. So I won't go into this, but I just want to say there's lots of opportunity for green hydrogen in the West across many, many sectors, driving investment and jobs, and it's going to be an important part of our economic future. And next slide. And I'll just go on to the next slide because I think I've covered why it's important to partner. We want to be in touch. We want to work with all of you to continue to drive momentum. I want to say that we did publish this year a Green Hydrogen Guidebook. Please take a look at it. Do connect with us. And also, of course, we welcome donations to continue our work. So thanks, Dan. Sorry, I went a little long.
Great. Thank you, Dr. Nelson. And I, again, will say that your guidebook, Green Hydrogen Guidebook, is an excellent resource and would really encourage folks to take a look at it if you're interested in green hydrogen.
Great. And Dan, there are a lot of appendices. Please feel free to make these slides available to those on the call, because I just want to emphasize green hydrogen is happening today. It's happening in the US with the largest power project in the world, but it's happening also across the globe. And I provided some slides on what's happening in terms of global activity as well.
Excellent. Thanks again, Dr. Nelson. And with that, I'll just turn the mic over to Mike Ducker with Mitsubishi Power. Mike, go ahead.
Thanks, Dan, and it's great to follow up here with Laura and all the great work the Green Hydrogen Coalition is doing, and to talk a bit more today about not only what we see with happening there, a bit more detail in Utah and why now around green hydrogen, but more importantly, the opportunity here in Montana as we see it. Before we begin, actually, just want to say, Dan, I'm having a little technical issues. My computer's randomly muting me. So if that does happen, I'm not aware of it. Just give me a heads up and I know how to fix the problem. So apologies for that. If we move to the next slide here. So Mitsubishi Power, we start off with our mission statement in that we will provide power generation and storage solutions to our customers, empowering them to affordably and reliably combat climate change and advance human prosperity. We start with this slide because on the next slide, what you'll see is really all of the product lineup and our focus within Mitsubishi Power is this changing dynamic and what our customers are demanding, what our customers' customers are demanding, in today's framework, and it really is around helping to solve reliable and affordable clean energy. And those are important aspects, right? We can't look at one independently of the other. We want reliable, we want affordable, and also at the end of the day, we're also looking to decarbonize across our grids. And so our product solutions that we bring to bear today really reflect this changing dynamic throughout our industry and our customers. And so we're offering anywhere from hydrogen-ready gas turbines, which I'll talk more about today, PV solar development and offshore wind, and then also getting into battery storage systems, both lithium ion as well as hydrogen. And Dr. Nelson started to touch on that. Really, this is kind of a changing dynamic, in a lot of people's minds see hydrogen as a fuel, when in fact, really we see green hydrogen, at least in the power sector, as a storage medium. And we'll talk a bit more about what that means, in addition to it being a clean fuel for other verticals like transportation and heavy industrials. Next slide, please. So before I go into a bit more on our project, do want to talk about what are we seeing right now in the energy landscape. And really, there's been two distinct phases of what we're calling what we call power grid decarbonization. And the first phase has been predominantly the retirement and replacement of coal-fired power plants and oil-fired plants with a combination of natural gas and renewables. And what most people don't realize is actually since 2005, we've cut carbon emissions in the power sector by over 40% just by this strategy alone of effectively retiring and replacing coal with a combination of gas and renewables. But in many parts of the United States and world, and actually even in places like California, we've already gotten to the point where we've retired all of our coal-fired assets. Yet the targets that we're seeking to decarbonize with these systems certainly go beyond 40%. So the next challenge that we see is how do we then look at addressing the emissions coming from natural gas-fired units, which historically provided the long-term intermittent balancing of renewables? How do we overcome that? And this is where we see a play for energy storage. And this is important to note too. I mean, again, Mitsubishi Power, really our flagship products and our background is natural gas-fired units. And so what we've seen and what we're embracing in this change is looking at how we can use gas-fired units to transition over time to really serve this deep decarbonization goal and really repurpose gas-fired units as an energy storage asset. And again, we'll talk more about what that means here today. Next slide, please. So when we think about energy storage systems, most people in the power industry are very familiar with lithium-ion batteries. And so on the bottom there, we see our typical really battery system. And there's three main components when we talk about energy storage. First of all, we need a means to control the charging rate, or basically taking excess renewable energy, and how do we convert that to a form of storable energy? And for batteries, we have a power conditioning system, really known as a rectifier here, which is converting AC to DC electricity, and now it's a form of storable energy. We then have a means to control the amount of energy we store, and in this case, we're using lithium-ion cells that are actually storing electrochemically the excess energy from renewables. And then lastly, we need a means to discharge that energy back to the grid. And again, a battery has a power conditioning system, though on the back end, we're now using an inverter to convert DC back to AC and provide that stored energy back to the grid. For hydrogen, we can have the same three fundamental aspects of a storage system, albeit a little different. For a hydrogen system, the means that we use to control the rate of charge, or basically taking excess renewables into a form of storable energy, we use an electrolyzer. An electrolyzer takes electricity and water, decomposes water to its elemental forms of hydrogen and oxygen, and now hydrogen is actually a form of storable energy. We can then store that hydrogen in salt caverns, in pipelines, above ground pressure vessels. We've actually been storing hydrogen at these scales since the 1980s in salt caverns, and we're able to store it, then in those different mediums. And then lastly, we have a means to convert that electricity, that stored chemical energy, back to usable electrical. And this is where a gas turbine or fuel cell can come into play. Now, one of the really nice attributes of hydrogen in this whole ecosystem is, prior to going to the gas turbine, this is really what Dr. Nelson referred to as the power to gas back to power. But from this stage here, if we had other offtakes or other interested entities trying to decarbonize, we could take that hydrogen stream, and rather than going to a gas turbine, it could go to, say, heavy haul transport or in a heavy industrial who is also looking to reduce its carbon emissions. Next slide, please. So why is this important right now? Why are we seeing today, hydrogen starting to really come back to fruition? For those who've been in the energy industry for some time, early 2000s, we were talking about hydrogen, but at that time, it didn't really come to fruition. And one of the major drivers behind there was just the market signals and what the requirements were back in the early 2000s versus where we stand today are fundamentally different. And one of those ways that we can look at that is actually, pointing to California, and where we see some of the initial projects coming to bear is around the balancing of renewable energy. And so what you'll see on the left graph here is a look of California. These are wind and solar curtailments since 2017. And the different colors signify the different years. And you're going to notice two important trends in this graph. The first trend is every year since 2017, we continue to have record year-on-year curtailments. And what that means is the more renewables we continue to add to the grid, the more we actually have to curtail or shut down renewables. Some of the in the industry refer to this as the cannibalistic effect of renewables, in that, if you have so much solar in the middle of the day, if you add more and more solar that you've already shut down, you just end up shutting down more and more solar. And so this is one of the challenges with renewables. As we start getting to higher penetration levels, we also run into the challenges of managing the supply and demand, and we oftentimes are met with oversupply at certain periods of the day and undersupply at other periods of the day or year. The other really important trend we can draw from this graph, though, too, is you'll notice is that there's a seasonality effect that we're starting to see with greater penetrations of renewables. And so from January through June of 2020, what you'll see is we've averaged about 150 to 200 gigawatt hours of curtailments, peaked in April at over 300 gigawatt hours. Yet in August of 2020 this year, we had our first rolling blackouts in over 2 decades in California. So what we're starting to see is the seasonal effect of we're long on energy in certain periods of the year, and we're short on energy in certain periods of the year. And if you look on the graph on the right, this shows it all the more that as we go to higher and higher targets of renewables and decarbonization, we're seeing this greater impact that I'm no longer concerned about my intra-daily management of energy. I'm more concerned now about my seasonal balance of energy. And so how do I take, in this example, could I have shifted April excess into August to avoid a blackout? And this is where resource adequacy and reliability and affordable ways of addressing energy really come into play, particularly as we start going beyond 30% types of targets, as evident here with California. Next slide, please. So this really helps introduce what Dr. Nelson started to talk about, one of the world's first and largest project around green hydrogen. It is the Intermountain Power Project. And so March of this year, Mitsubishi was formally awarded the contract for 2 hydrogen gas turbines for the Intermountain Power Project. This will be an 840 megawatt combined cycle power plant that in 2025 will run on a blend of 30% green hydrogen and 70% natural gas. And by 2045, the asset will be really, again here, repurposed to be 100% green hydrogen. And this is all to support California's goals to achieve carbon neutrality by this time frame. And so one of the unique aspects here, what you'll see is we're transitioning over time. So we're not saying in 2025, this unit has to be 100% green hydrogen. We recognize, and certainly in this case, our customer recognizes, that costs are going to come down over time. But today we need affordable, reliable, dispatchable energy. And this is where the natural gas piece comes into play. And over time, as we build more and more renewables, and as our grids require more and more deeper decarbonization, and as a result, more resource adequacy and reliability improvements, we can transition this unit to run fully on green hydrogen and take advantage of that energy storage technology ecosystem, if you will, that I talked about in the previous slides. And so again, here, the big benefit from a planning standpoint, from ultimately the impact to ratepayers, is our ability to provide this asset today to provide affordable, reliable energy, and over time still meet the type of decarbonization goals that our customers and utilities and different entities are demanding by the turn of the next 2 decades. Next slide, please. Right adjacent to the Intermountain Power Project is our Advanced Clean Energy Storage Project. And so Mitsubishi Power invested with Magnum Development in the salt caverns and the development of green hydrogen infrastructure right adjacent to the Intermountain Power Plant. And so this project here really is us working to develop beyond just the gas turbines, but actually the hydrogen production and hydrogen storage infrastructure that will be necessary to achieve a lot of the goals that, again, many of the states in the West and really across the United States are targeting to achieve in resource adequacy and decarbonization. Next slide, please. So what's unique about our site here in Delta, Utah, is that it's the only Gulf Coast style domal quality salt dome in the West capable of large caverns. And as I started mentioning earlier, we've actually been storing hydrogen at large scales in salt caverns since the 1980s. So this is nothing new here. We're actually just looking to apply this rather than the refineries and petrochemicals industry looking to apply this storage of hydrogen to support the power industry. The site itself is centrally located to the Western Interconnect. We've got high voltage DC lines into Southern California. There's also major transmission lines being proposed from Wyoming on down right through our site. And we see this as a great opportunity to really help the West achieve some of its decarbonization goals, not just in the power sector, but really beyond the power sector too, whether it be transportation, data centers, even military and beyond. And so if we go to the next slide, this is where we started to talk about the idea of how do we really achieve these goals of across the West, and not let this just be an opportunity, say, for the Intermountain Power Agency or entities covering in the Southern California. And so what you see on the left is this is a slide I think that's been somewhere throughout within the public domain. But if we start in Delta, Utah, which is where we see the opportunity for bulk storage of hydrogen and renewable energy storage, really the business model or the case here is looking at taking bulk curtailed renewables from Southern California along a high voltage line there, using those salt caverns to store excess renewables. And then when that firm dispatchable carbon-free energy is needed, we can run that in gas turbines there at the Intermountain Power site or other sites throughout to provide that needed energy within Southern California. And so we began to ask the question, what other parts of the West and how else can we achieve this model throughout the Western United States? And this is where the idea of looking at connecting infrastructure between Butte, Montana and Delta, Utah could provide that opportunity. And now we look at Montana really positioning it as an opportunity to help the Pacific Northwest states also achieve their goals in decarbonization, and really look at more of a region-wide approach to achieving resource adequacy, as well as the environmental targets that are being assessed or pursued, I should say, by each of the states and each of the utilities. And so next slide, please.
And just 2 minutes left, Michael.
Okay, great. So really just going through the last few slides, in Montana, we saw not only the opportunity within Northwestern Energy and some of the challenges with retiring Colstrip's units 1 and 2, as well as some financial exits forthcoming with the Colstrip asset. But also, if we look at the opportunities with the Berkeley pit, I mean, one of the things with green hydrogen is we do need water. And in this case, we saw an opportunity with the Berkeley pit where we were already treating up to 10 million gallons a day and really to protect the Clark Ford watershed. And so it became a question, I think one of the newspapers in Montana talked about, really turning lemons into lemonade. Can we take this, what's otherwise been an environmental challenge, and turn it into an environmental opportunity? And, can we take this water then, use it to actually help provide green hydrogen in support of projects we've got within the state? Next slide, please. And so really the last slide I'd end on here, and I think the few others to talk about some of our projects, is this idea of a hydrogen center and really a hub in Montana. And the opportunity as we see it is it positions Montana as a national leader in not only resource adequacy in decarbonization, but also in resource adequacy and how to reliably and affordably achieve this. Like I talked before, turning an environmental challenge into an environmental opportunity. And Dr. Nelson started to touch on it too, but this really creates an opportunity too, if we look at creating hydrogen infrastructure to attract new regional green industries and jobs, and also demand growth. And all this can be done too from the long term, but in the short term, as we look at near-term capacity and energy needs, we can still provide that affordable and reliable energy and transition these units over time from partial gas to eventually 100% green hydrogen, exactly like the Intermountain Power Agency is doing with their asset down in Delta, Utah. And in connecting these infrastructures and looking at doing this from a region-wide standpoint, as opposed to just individual entities within a state or within a city, we're able to achieve a lot more of these economies of scale. And this is really the last point I'd probably make here. And I've been to Montana many times, and Butte and Montana as a whole really was the hub that helped electrify the world a century ago. When we look at the copper mining and the opportunities there, and now we're really looking at this as an opportunity to position the region also as a hub to bring green hydrogen to the world today. And so with that, I think we can pause here, and the last few slides are just some other backgrounds on projects that we're working on, and would rather spend time answering questions and talking here with the panel.
Great. Well, thank you, Michael. And thanks again, Dr. Nelson, for two really great presentations. We've got a couple questions from the audience that I would like to get to first, and then I've got a couple myself if we have time. So Andrew asks, what kind of losses are you experiencing in transportation and storage? And I'll leave that open to both of you if you have answers for that.
So maybe I don't know if we can clarify quickly, but losses as it return to, would say leaks, or losses in regards to, we'll say efficiency, round trip efficiency impacts. Is that something we can clarify quickly?
I'm thinking it's with respect to leaks. Okay.
Yeah. So, I mean, I guess it goes back to understanding, like I mentioned earlier, we've been storing hydrogen at large scales since the 1980s. We've got over, most people don't realize, 1,600 miles of hydrogen pipelines throughout the US. Most of those are in the Gulf Coast, but several of those are in major cities like Los Angeles and Salt Lake City. And so as with any infrastructure project, we're always careful or concerned about leaks or environmental issues. The great news is, though, we can rely on these decades worth of history in the US, where we have been successful in mitigating any leaks or concerns or impacts, as we've seen, again, going back as far as the 1980s. Here in the U.S. I don't know, Dr. Nelson, if you have anything else to add.
I think just the one thing I would add is that the hydrogen fuel doesn't degrade as a fuel source, and so that's really important. So other types of fuel sources like diesel, you really have degradation over time. So looking to use hydrogen as a drop-in fuel replacement for diesel and backup generators is very, very relevant, because oftentimes you have long periods of time between when you establish backup generation and when you actually have to use it. So if you just look at, for example, fires in California and the need for resiliency and recovery from those situations, you need those generators to be available, and you need the fuel to be available. So that's definitely a place where hydrogen, green hydrogen, can play a role, and so it doesn't degrade like other fuels can.
Great. Thank you both for that. And we've got 1 minute left, and just one more quick question I think we can get to. Representative Heyman is asking about what the cost of hydrogen power generation is relative to wind and solar. And it's probably not a 1 minute response type of question, but Michael, I'll let you kick it off.
Yeah, so I'll answer that very briefly. The most important aspect to understand is hydrogen is not competing against wind and solar. It's helping to more cost effectively integrate wind and solar. And so we look at hydrogen just like we look at batteries. They're energy storage systems, which are looking at, again, more cost effectively, reliably integrating other assets, generating assets that are, we'll say, more intermittent, in this case, like wind and solar. So we actually really compare more levelized cost of storage as opposed to what we'd say levelized cost of electricity, which is your traditional way of looking at wind and solar assets. Just in short, what I'd say is when we look at batteries versus hydrogen, both will be necessary. Batteries are much more adept and capable of short duration, intra-daily management of renewable assets, whereas hydrogen is much more adept at inter-daily, longer duration impacts of renewables.
And Dan, if I could just add, once you pass about 12 hours, the cost of hydrogen storage beats the cost of battery storage. So it really is looking at that across days, weeks, seasons, that we're going to be in need of this long duration resource.
Great. Well, thanks again to both of you for being here today. And I apologize. We had a number of questions that we weren't able to get to. And if it's all right with you, Michael and Laura, I might follow up in an email with some questions if you would entertain responding to a few more questions.
Of course, would be happy to.
Yeah,
Great.
same. Great. Please feel free to share my information and my slides.
Thanks. And with that, I will turn it over to Kyla to introduce our second panel.
Thanks, Dan. Good morning, everybody. So our next panel is going to highlight innovative projects and demand-side programs that are helping Montana utilities reduce capacity constraints, improve reliability, and save their members and customers money. As more intermittent generation resources come online, it creates opportunities to address grid reliability and capacity constraints through new and innovative ways to deliver energy to consumers. We have 4 great panelists that will discuss projects and demand-side programs that are helping their utilities meet some of these challenges and adapt to the changing energy landscape. So our first panelist is going to be Darcy Negum. Darcy is the current Director of Electric System Operations and Planning for Montana Dakota Utilities. He is responsible for the planning and operation of the company's electric transmission system, as well as the company's electric resource planning and power marketing activities. Darcy has been with Montana Dakota Utilities, MD Resources Group for 25 years. Darcy?
Thank you, Kyla. Good morning, everyone. Just briefly, Montana Dakota Utility does serve electric and natural gas customers. On the electric side, we do serve customers east of the Forsyth and Miles City area. So next slide, please. When we talk about doing utility resource planning, we have to look at how do we economically and reliably meet our customers' both peak demand and also their hourly energy requirements, and come up with a balanced system to find the most effective way to do both of those requirements. So next slide, please. When we talk about meeting peak demand requirements, that's for the peak, hottest day or coldest day that we would have on our system. And so when we look at that and we talk about dependable generation, that we have to have at the time of our peak system requirements. So either that comes from dispatchable generation that we would own or contract with otherwise, and we get credit for that at the time of that system peak, which may be different in the summer and winter as far as the requirements we receive. And if we're talking about intermittent generation sources, renewables, wind, solar, we take a look at what's the expected generation we would expect to receive under those peak conditions. A third way that we can look at meeting our peak demand requirements is what can we do for customer load programs. And historically, those have either reduced our load requirements being net of, or we could consider those to be a supply side resource as well, as far as something that we're integrating into our portfolio of resources. And when we talk about customer load programs, we're looking at compensating customers to be able to reduce their load during these peak events, or maybe under an emergency condition that we would have. And we would do that economically as a way versus building new generation or purchasing these same capacity resources from another utility. Next slide, please. So historically, we've had for probably over 20, 25 years, customers who have directly participated with Montana Dakota Utilities as an interruptible customer on the electric side. Historically, we contracted with those customers directly. And so we would have had to have the communication means in place to tell them to interrupt their service and when to come back on. Typically, those customers did own on-site standby generation. They likely also were responsible to supply any of the fuel needed to run their generation during an event. Customers also may have had hourly limitations per year on participation, and they may have been assessed a penalty if we would call on an event and they did not participate. The way that we would generally do the direct contract customers is they would go through a special utility service rate that we would end up having. Next slide, please. We talk about the novel approach that we had. It's probably about 7-8 years ago. We did look at, rather than just directly contracting with customers ourselves under our tariff rates that we would have, in this case, rate 38, but to go through and to find a novel way to get smaller customers to be able to participate, and at least those maybe we historically wouldn't have targeted ourselves. And so we did this through a power purchase arrangement that we would have with an aggregator of demand response services. And so we looked in this program to target either load-only customers or customers that were smaller and had smaller standby generators as a part of their service that they would have. Next slide, please. When we talk about meeting any demand response or capacity resource programs, we have to take a look at requirements for any of the capacity sharing groups that we participate in and make sure that if we establish a program, it meets with those requirements. In this case, we participate in a regional transmission organization, which would be known as the Mid-Continent Independent System Operator, or MISO, that would run the capacity sharing group that we participate in. So when we looked at designing our program, we looked at what their requirements were, and then also what sort of customers were we targeting. When we looked at any of our non-residential customers, so they would be small and large commercial and demand customers, we were looking for those customers that had loads greater than 50 kilowatts. And the requirements that we had for participation is customers would have to agree that they would interrupt their loads for up to 4 hours per day. We also would look to have a minimum notice of an event of 1 hour, as far as for a customer to start their interruption service, and then an hour also to be able to come back and receive service from us. We did have limitations on participation for 50 hours per year, and also had requirements that customers would participate in seasonal tests. Next slide, please. One of the unique pieces or benefits for us in using an aggregator is that aggregator was responsible to go out and sign up customers and also contract them with how they would participate in a program. Similar to a power purchase agreement, there is a fixed demand rate for participation. That would be the availability of a resource that we would end up paying. And also, if there was an interruption in service, there was also an energy rate during that period of time that would compensate customers or businesses for lost business opportunity that they may have. Rather than all of the dollars going to our customers who participate, there is kind of a split as far as how much goes to the aggregator in this case, and then also to be able to run or have an administrative service fee. And then also the majority of the dollars do go back to our customers and as far as in their participation. And that's in the 70-30 split that I show on the slide. Next slide, please. So when we talk about the demand response aggregator, they do work with potential customers that we identify and give customer lists for, and they work with these customers of what their potentials might be. Now, a number of these customers already have energy load management systems that they may be able to incorporate into their participation, but generally the things that they're looking at is how can they control lighting, heating and cooling. Maybe they have a standby generator, or they're just looking at completely shutting a process down that they may have. And so the aggregator does work with the customers to understand their responsibilities, to put together their curtailment plans that they would have. And also they're the ones who directly work with the customers during an event to get them the start and stop signals. And that way we're not having to spend that time ourselves during either a system emergency or high peaking event to be making a lot of customer calls. And then also the aggregator is responsible for any of the contracts and billing that are a part of this program. Next slide. When we started this goal, this project and the goal we had, which was in the 2012-2013, we had targeted, at least the hopes of maybe getting to 25 megawatts, at least the participation on our system. We did have quite a bit of interest early on, and participation was slow in the early years, but we actually were able to achieve our target we had of 25 megawatts of participation here a couple of years ago. When we talk about the types of loads that participate, we're looking at schools, hospitals. We do have at least one nursing home that participates, a bank, a jail facility, some oil field loads, and industrial processing customers. One comment I would make on this participation is one of our customers had a standby generator. They did participate, and one of the things we've seen is they've looked at their supply requirements. They've installed some solar panels on the top of that facility. And what we end up seeing is most of our events, particularly in the summer, do occur the highest temperature days when the sun is shining. So the installation of the solar panels has, benefited them as far as in reducing their amount of service they take from us on an energy basis, but it also has reduced the effectiveness or their participation in their program. And so it's had kind of a counter impact, at least to them, of mitigating or reducing their participation level in our program, particularly in the summer. So this is a list of our customer loads. We did achieve our 25 megawatt target here back in 2018 and 2019. Next slide, please. So recently we've looked at expanding this program. We think there probably is an ability to participate, probably between another 15 and 25 megawatts. We did expand our contract with our aggregator for another 25 megawatts for a goal. One of the other things we're looking at a novel way to do is customers who participate, there has to be a way for the aggregator to be able to have a metering system and also communication system to monitor what our customers are doing. And generally that's one of the customers' participation cost responsibilities is they're responsible to either pay for or reimburse the aggregator for that equipment. One of the things we've seen is it kind of does diminish the ability for small customers to participate. So in the expansion of our additional 25 megawatts in our program, we've tried to work with and structure a way that they can participate and at least reduce those install costs through a number of participations with our aggregator. Next slide, please. So currently, when we talk about meeting all of our customer peak demand requirements, about 7.5% of the resources that we need in doing that do come from customer programs today, either through the direct contracted ones that we have or also through the aggregator program. What we're looking at doing is probably increasing that number from 7.5 up to 10% as far as to the expansion of this program. And we hope to be able to achieve that here over the next probably 3 to 5 years to get to our additional target levels that we do have. Now, we can't explicitly build all of our system to use customer interruptions. We do have to have other resources available. So we do think the 10% is at least a good balance. Certainly the peaking resources we have, and especially the last ones we build to meet the last requirements, do run just a very few hours of the year. So, customer participation program, certainly it does avoid dollars that we would have to pay for either other resources we own or to spend with others to have that capability available on those peak days and conditions. Next slide, please. And lastly, I do want to touch on beyond the commercial industrial programs, we do have other demand response programs historically. These are the ones on the residential side, which typically, because the loads on an individual basis are smaller, we don't quite get as much bang for the buck. But we have had or do have programs in place for electric storage and hot water heaters. We have looked on the residential side for air conditioned cycling programs. Those have not been cost effective as compared to other alternatives. And generally the involvements of these programs have either involved timers or as far as physical control devices for interruption. Next slide. And Kyla, that's the end of my presentation.
Great, thank you, Darcy. So next we have a couple representatives from Northwestern Energy. First we have Brandy Hellwinkle, and Brandy has worked for Northwestern Energy for over 10 years, where most of her time has been spent in different aspects within asset management. Currently, she leads a team of engineers and data analysis that are responsible for development of system strategies and standards for electric and gas distribution. Brandy works in Bozeman, Montana, but has responsibilities across the company in Montana, South Dakota, and Nebraska. She has a BS in civil engineering from Montana State University and is a registered professional engineer in Montana. And then we'll have John Schaefer. John Schaefer is manager of system innovation for Northwestern Energy. He received his BSEE from Montana State University and an MBA from University of Montana. He has 13 years of experience with energy efficiency and renewable energy projects. His work involves distribution, SCADA, distribution automation, volt VAR optimization, microgrid technology, LED street lighting, advanced metering infrastructure, and advanced distribution management systems. So Brandy, if you want to go ahead.
I'm actually going to kick off the first couple slides here, and Brandy will jump in on some of the analytics. But next slide.
Great.
And thanks all. Again, John Schaefer, looking forward to this. So in front of this, we have this journey map that we put together. And again, Brandy and I both work in the distribution side of our business. And so when we're looking at this, we're trying to set up the distribution. So a lot of this is, how do we keep the energy affordable, reliable for our customers? And so you can kind of see some accomplishments. Again, we mobilized our workforce. We're standing up what's called an ADMS. I'll talk about that. But transitioning to a distribution control center. So how are we going to maintain all these new technologies in the future, and how do we have central oversight over that for safety and reliability? Making sure we're setting our field equipment up, so distribution equipment's automation ready. And then we have some pilot projects we'll talk about. Moving forward, again, we're going to continue deploying on that technology to basically make our system more efficient, make our workers more efficient, increase our customer experience, and then create actionable data from all the data from all these new technologies. And going to our right here, really there's three platforms. There's an energy management system that we've had in place for a long time that manages the transmission system. We're currently in the process of deploying the next two pieces of the puzzle, an ADMS system to give us central oversight, and an AMI network to give us a very cost-effective communication to all our customers, and also a lot more data to figure out how do we develop the right programs for our customers. And so, on the left, you have a lot of opportunities, expectations, renewable, DERs, energy storage, environmental stewardship. We're getting a lot more data. We're trying to kind of fill that pie chart out on the right. How do we provide more customer services? How do we meet needs of supply moving forward, transmissions moving forward? And how do we be more efficient in our distribution services? So that's kind of the overview we'll talk about today. Next slide. So, as we move forward and create programs, we got to think, how do we change the utility? How do we set up the right platform so we're successful in the future? So next slide. So as you can see today, we have, we've had this in place. It's the energy management system. We produce power wherever it may come from, and we supply customers with energy. We have to maintain balance, just as others have talked about. And it definitely varies throughout the year of how we do that. And so that's kind of today's, and then what we're kind of implementing. So next slide is two pieces. One is called Advanced Distribution Management System. And so basically what we're trying to do is understand where energy is going on our feeders, understanding where outages are occurring, getting a higher level of control on the distribution side of the business, and also train a new workforce to kind of manage that real-time distribution situational awareness. And so we're upgrading our substations or switches out in the field, and then where we're trying to get to is this real-time power flow model that's predicting where the energy is going, and we can predict where outages are with that model. And then we're also working on AMI. We deployed AMI in South Dakota. We're looking at deploying AMI in Montana, this next coming year. And so, with that, now we have a system to feed outage demand data back to the system, energy and voltage information back to the system. And so this is kind of the new foundation, that we're gravitating towards. And so the question is, what does that enable? So if you click on the next slide. So one concept is, we do need more generation. We need to, especially in the peak times. And how do we do that in the summer? How do we do that in the winter? We're still a little bit of a dual peaking utility where we have the super cold days that you know, the sun's not shining, but also the wind's not blowing, you know, and it's just super cold outside and our energy peak is high, and we need to be able to serve that peak for a longer duration, and that's difficult. But the possibilities here is now, you know, like a demand management program. How do we now control load to match supply? How do we think about that differently? And how do we create that foundation platform to do that? So we got the advanced distribution management system, but then that provides controls. How do we do energy storage? There's fault location isolation service, bringing customers back in faster out of outages or from outages. We got demand response. Again, how do we adjust loads? Do we want to do that on a local level because there's local issues, or do we do it on a system level because there's supply issues? How do we optimize that? How do we think about volt bar optimization and ability to adjust loads, make the system more efficient? And then what do we do with AMI data? You know, how do we affect behavior with aligning rates? How do we provide outage information to respond faster? How do we provide voltage information so we can really tune in a volt bar optimization program? So those are the things we're kind of thinking about. We piloted a lot of this technology singly, but not comprehensively. But this is kind of the big vision. So next slide, we'll jump into some of the data stuff we're doing, or I guess we got 2 more slides here, and then I'll jump into the data stuff with Brandy. So we got some pilots of some standalone storage. You know, we're looking at storage. How do we locate that for our rural customers? How do we increase reliability? We have a lot of line exposure, and then we can control that localized energy storage on kind of a 1-by-1 basis to provide local voltage support, reduce local peaks, and balance kind of the on-site variations of renewable energy. And when I say energy storage, I'm thinking, you know, 4 to 8 hours is kind of the key to energy storage of where it's valuable, of providing enough energy for 4 to 8 hours. So I'm not talking about larger supply and meeting long duration peak. That might be a different technology. But next slide. And then the next broader concept, you know, we'll talk about is, you know, how do you aggregate that storage? So now you can really affect supply. Again, kind of that 4 to 8 hours of reliability. How do we shift that renewable energy and manage that peak on a day-to-day basis? How do we offset some of the ramping needs as we start seeing more renewable energy on our system? You know, how do we maintain frequency response on a generation supply kind of level? But this is all kind of future stuff, but you can kind of see all the business benefits stacking up here of how do we optimize storage or even demand response programs to really change and control loads instead of just providing more supply. So that's kind of the concepts with some of the overview of where we're trying to head with our company. So next slide, we'll talk, I'm going to hand this over to Brandy and talk about how we're starting to use data. So go ahead, Brandy.
Thanks, John. As Kyla said, Brandy Hellwinkle, what my team is responsible for is really looking at the data, putting the data to work, and then developing the strategies for some of these innovative solutions to understand what are the benefits, where should these go into place, what type of solutions are we looking at. So next slide, please. We really like our journey maps here at Northwestern Energy, so I'm also going to cover a journey map real quick here. I thought it'd be good to explain kind of where we've been and where we're headed. In the 2011 timeframe, as Northwestern Energy emerged out of bankruptcy, kind of our primary focus was to reestablish our asset profiles, reestablish some of our proactive programs, and make sure that our assets are performing as we would expect. Along with that proactive strategy, we really re-looked at what our performance metrics should be, kind of how we want our system to operate. About midway through that 7-year program, we decided to enhance the program to include some technology considerations to really set us up for this future grid that we're talking about. So we enabled a pretty large communication platform. And at that time, we started putting in smart switches and other SCADA devices to start enabling getting that data out of our system to understand really what's going on. A couple of years ago, we transitioned out of that proactive program and more into this analytics phase. So now that we have all of this data from our system, how can we analyze that data to make sure that we're coming up with the right solutions and the most valuable solutions for our customers? We're probably about 90% through that phase, and we're starting to get into this optimized phase. And really what that means is with the AMI, ADMS that John just covered, and kind of getting more data, more live data into our analytics processes, how can we evaluate that data and really set up our system to say yes to our customers, and what type of innovative solutions can we put into place that may be more valuable to our customers instead of more of a traditional reliability or capacity type approach. Next slide, please. This is a zoomed in slide of kind of where we're at in that analyze to optimize piece. It covers some of the platforms in which that we're utilizing to get to the optimized piece. John just talked a little bit about the AMI project. Obviously, the more data that we have, the more real-time data that we have, the better our analytics is. We are also utilizing some advanced analytic tools to start doing some machine learning, some predictive analysis, again, just to strengthen our overall concepts on where we should be applying these solutions and what type of solutions are we really looking at. Next slide, please. So from a utility perspective, we are a medium-sized utility here in Montana. We actually perform pretty well from a reliability perspective. We are within the first quartile. You can see on this graph that over the last 5 years, our reliability is trending downward. So we're actually improving. The blue lines are our distribution related outages. Those tend to be trending downward because of some of the proactive projects that we had already done with that program I just talked about in the 2011 timeframe. But when you look at the orange lines, those are our transmission related outages. Those are pretty level and even trending upward in some cases. So some of the places that we're looking at a more innovative solution compared to a traditional, more costly solution are really trying to minimize our transmission outages, utilizing storage to try to offset some of those transmission related outages to keep our customers into power. Next slide, please. So we've just kind of started trying to roll together a more global program for DER and other storage applications. Right now we're focused on the distribution system, but also trying to tackle those transmission outages I was just talking about that cause distribution customers to go out of power. So when we look at where is the right place to install some of these storage solutions, we're trying to look at the reliability, but also look at what is the value. We've started bucketing these into kind of 3 different categories. So first and most obvious is reliability. Obviously, we want to improve customer satisfaction, keep customers into power. There is some residual benefits as far as the restoration piece of an outage with a storage application. The deferral of any traditional capacity solutions. So instead of rebuilding a substation or adding an additional substation, can we utilize storage to defer those more costly capacity solutions? And then the third bucket is still in development. It's pretty generic at this point, but we know that depending on the location that a DER is installed, that there's a lot of system support value that comes along with that, whether that be power quality or other metrics that we evaluate. There is some support that DER provides to our overall system. Next slide, please. I'm going kind of fast because John's going to talk about some of the pilot projects, which is probably more fun than talking about data. But I did want to show a screenshot of one of our dynamic dashboards. This is an advanced analytic tool that we're using here at Northwestern Energy. The software is called Tableau. Essentially what it does, it's a giant pivot table that feeds multiple data sources with a live connection and enables us to do a variety of calculations to really try to understand where is the appropriate placement of some of these innovative solutions. Next slide, please. So at Northwestern Energy, we actually have more miles of distribution line than we have customers. So one of our big challenges is really trying to improve our rural reliability. A lot of times a traditional solution, such as going from overhead to underground, is very costly, especially in these rural areas. So we see some huge potential here with some more innovative solutions, such as storage and DER, to help improve the reliability to our rural customers. Next slide, please. I just wanted to share this slide as well. My team's done some great work on really putting this live data to work. And what this is showing is a tool for our engineers to use to understand, okay, we have a distribution problem. The circuit that's shown here is a 180-mile circuit in our Bozeman division. Where are our outages occurring and where would be the best placement for that DER? So now that we have available data that's live, we can really understand what portions of our feeders are going out of power, what's causing those outages, so we can in turn apply the appropriate solution to mitigate that reliability concern. That's all I got on the data side. I'll hand it back over to John to talk about the fun stuff.
Thanks, Brandy. And you know, we'll take questions, but I know I've been kind of pushing through these slides because we have a few. So anyways, projects that we're currently working on or have in place. We have the Beck-Hill microgrid. So this goes along with rural reliability, 80 kW, 200 kilowatt hours. It automatically operates during outages or customers go back into power after, you know, probably experiencing a short duration. You know, we wait for the recloser to operate 3 times before we engage this asset. So anyways, it's operated 12 times pretty flawlessly. Powered customers over 4 hours. We have renewable energy that helps offset just kind of the, you know, keeps the batteries charged. It also goes back up onto the grid to support the local customers once the batteries are fully charged. And as Brandy said, we're looking at a whole bunch of different kind of larger applications. How do we scale this? How do we affect reliability? What makes sense? You know, look at Twin Bridges, White Sulphur Springs, 320 Guest Ranch, some of our places where the businesses, they're starting to rely more and more on energy. How do we provide that reliability? And so again, that's 3 megawatts, roughly 12 megawatt hours of storage. And then we're also looking at Beckler Ranger Station, so an off-grid power plant for the park. We also are looking at Helena Pilot, which basically says, you know, maybe we can locate storage at every transformer, so those customers never experience on a transformer by transformer basis, never experience an outage. And then we can aggregate that small, you know, storage up together to really support the system. So just some different pilots we're working on. Next slide. This is the Bozeman Solar Project. We have advanced inverters. We have the controls, you know, enabled. We don't really use them too much, but enabled to do curtailment, VAR support. We also have AMI metering and about 60 customers in Bozeman that's providing us 5-minute data. So we could really align solar production with customers' load and demand and understand, you know, does renewable energy help that customer's peak? And it kind of depends on whether that's a residential customer or a commercial customer of how they use energy. And so just kind of exploring that concept. We have the Missoula Solar Project where we worked with each high school, installed 4 different solar systems, different inverters, different solar panel technology, bifacial panels. We actually brought the solar down and made a solar fence at one of the schools. That's the bottom right corner. So how do we use existing structures to locate, you know, energy at the source? Next slide. And then this is our West Sump project. It's an off-grid power plant featuring energy storage that's more of like a hybrid battery capacitor based that's supposed to have a very long life, operate a wide operation, in a wide temperature operation. So we're testing this technology out in the park and see if it makes sense to scale this technology larger. It's a company called Kilowatt Labs. They're based out of Dubai. So that was put in the summer, has worked flawlessly. It's powered a ranger station throughout the summer with 0 outages, and even though the park had outages, their ranger station stayed in power 24/7. So we're going to continue operating that in the winter. We're not heating or cooling those batteries. So all those ancillary loads that usually come with lithium ion types of storage, we've taken those all out, and we're gonna really test these things out. The park gets extremely cold, and we're gonna see if there's any reduction in performance of the storage. So yeah, interesting technology, fun time to be in with the utility. But I think we're about out of time, and I think that was my last slide to talk about.
Thanks, John and Brandy. Really good information and some interesting projects. So just as a reminder to everybody, if you have questions for any of the panelists, please feel free to type them into the chat box, and we'll we'll answer them after our final panelist presents information on what Missoula Electric Co-op is doing. So we have Dan Rogers with Missoula Electric Cooperative. He is the Energy Services Specialist with MEC. He's been with them for 13 years, managing their energy efficiency programs for the past 10 years. As the Energy Services Specialist, Dan will expand the organization's focus on new technologies, challenges, and opportunities in the area of energy. So if you want to go ahead, Dan.
Sorry about that. Thank you, Kyla. I'm going to be talking kind of from the cooperative perspective on what we're doing with energy efficiency and some of the projects that we're going to be looking at. Just for a frame of reference, we are the 3rd largest electric cooperative in the state of Montana. Our service territory goes from the west in Superior to the east in just about Avon, north to past Condon, almost to Swan Lake. And then the south, we go down to Bass Creek, which is south of Florence. We also cross over into Idaho on Highway 12, or yes. So we serve about 13,000 members and 16,000 meters, and we have 2,000 miles of line. So as you can imagine, it's pretty low density, and we have, our special set of challenges with operating in a rural environment with that many miles of line and maintaining reliability, which we work very, very hard to do. So next slide. So what I want to talk to, about the group, the group first is really this, what we're doing in the area of energy efficiency. Energy efficiency is really our bread and butter, for energy conservation. We don't have a demand response program. We focus on the energy side with our consumers. Part of that is, we are a member-owned cooperative, so we are responsive to our members and what they want, what they ask for. And our members, do want to save energy wherever they can. So we offer programs in the residential, commercial, and agricultural spaces. And as you can see on the left, we really view energy efficiency as this least cost resource. Next slide, please. So in our residential sector, primarily, we do the weatherization, the HVAC, and the water heating. With weatherization, we have programs for standard and low income weatherization involving, adding insulation and air sealing and replacing doors. In the HVAC area, we focus primarily on heat pumps, ductless, air source, and ground source heat pumps as well. And then in the water heating area, we've really expanded into this heat pump water heater technology. So next slide. So, regarding heat pumps, these, heat pumps, a little history on them, they came about really as a response to the energy crisis in the 70s. And the heat pumps that came out are they share a little bit in common with the cars that came out in response to the energy crisis. They weren't very good, but in that time frame, since then they've really come a long way. Heat pumps have been operating obviously in the South and Southwest for decades, and have been very good for cooling in those areas primarily, but also handling a little bit of heating with the mild temperatures that they get in the South. What we've focused on in the Pacific Northwest through organizations like NEA and Bonneville Power Administration is really pushing the efficiency of heat pumps for this cold climate. And we've really come a long way with these technologies. Just to give you an example, for ductless heat pumps, that's a great technology that's been around in Japan and Australia. It's really the standard there, but we haven't seen it be adopted widely in the United States. Those units are now achieving coefficient of performance of 2, which basically in layman's terms means for every $1 of energy that you put in, you're going to get $2 of heat out of that. And one of the things that they've really been working on hard with the ductless heat pumps is pushing that temperature range down as far as they can. So we've seen multiple manufacturers' units now achieving still more than 100% efficiency for every $1 of energy that you put in down below 10 degrees, below Fahrenheit. So of course, that's not the majority of our load. The majority of our heating load is going to be more moderate than that. And that's really where the energy savings comes in for these ductless heat pumps with 3.5 coefficient of performance in the 32 degrees Fahrenheit area. So that's going to be a lot of the heating time that we focus on in our area. The savings on these can be 1,600 kilowatt hours per year. That's really in comparison to a zonal electric system. This is talking really on a single head pump. And then if you compare that, if you're putting that in to offset, some of the electricity that's used by an electric forced air furnace, you can see the savings jump up by, another 900 kilowatt hours a year, making for, good payback. On the air source heat pump side, we've also seen coefficient of performance, increase on those. And right now we're seeing systems that are, running, north of coefficient of performance of 3, which basically that puts them in the neck of the woods of ground source heat pumps from 10 years ago. So the ability to extract heat out of the ambient air with these units has really come a long way. And there again, great savings for our members, over 6,000 kilowatt hours per year on those units, make them an attractive option. Next slide, please. With water heaters, it's really probably your second biggest energy load in a residential setting. And we've seen the infiltration of the heat pump water heaters in our area, and we've really pushed back hard with organizations like NEA to really work on the efficiency in cold weather climates. And as a result, we are seeing units, tier 2 and tier 3 units that have come to market. You can buy them right off the shelf at Home Depot that are really ready for the cold weather climate. And these units, they're saving 1,300 to 1,500 kilowatt hours a year. So they're a great option for people that are looking at replacing not only, an electric storage tank, that may be older and may only be in the 90% efficiency. But they're also a great option for people that are heating their water with propane or, if they're using a boiler with fuel oil, because electricity is such a more stable fuel cost. And then you also got to look at the regulatory environment. Really, after 2015, water heaters, as we know them, changed dramatically. We really had to look for units that were more than 100% efficient, and that is really what brought these heat pump water heaters to market. And also, you know, there's a limit on the size of the tank that you can even install in anymore on just a straight electric resistance tank. So if you're looking for something for a family of 5 or more or something like that, heat pump water heaters are really your only option. But you know, through the work that's been done in the region, they've, you know, really become a good option on their own. Next slide, please. In the commercial sector, you know, we've really focused our efforts a lot in the lighting space. You know, I'm sure most of us have LEDs in our home at least somewhere. But in the commercial space, it's been a challenge to work with consumers to see that it really is a good investment. They've been you know, less likely to take up the technology, just in my experience, because you know the scale of their project is much more costly, and they're looking for good paybacks. And really, when it comes to, you know, kind of the innovation in the area, what we're looking at is really these lumens per watt. So when LEDs first came to the market to deliver white light for spaces, they really were, you know, they were south of 100 lumens per watt, and we've seen that to rise to an area now where we're upwards of 200 lumens per watt, you know, commercially available fixtures. And there's, you know, a theoretical efficiency out there, you know, a practical theoretical efficiency of probably reaching 400 lumens per watt, which means that for all those consumers that have done lighting replacements and updated to current LED technology, they will theoretically in the next, you know, 5 years be able to go back and provide the same level of light that they're getting right now with, again, half as much energy as they're using today. Another area that we, you know, are seeing some penetration, some good technology coming into our commercial spaces is the variable refrigerant flow systems. The way that I like to describe these they're kind of like a ductless mini split on steroids. And one of the nice things about them is you have an outdoor unit and you have multiple indoor units. So you've got a lot of zonal capability for saving energy inside, but they've also made these indoor units very, very smart. So they're equipped with both thermal eyes that can scan the room, making sure that the space is heated evenly. They also come equipped with occupancy sensors. So, you know, if you have one located in, say, a conference room that's not being used, it will kind of go into an away mode if there's nobody in there. And then they can combine those two technologies, you know, so that even if you have people occupying a large conference room, if everybody's sitting on one side of the room, then it's not going to heat the side of the room that's empty. So we've seen that one of those systems go in our area and seen very, very good efficiency from those, and probably hoping to see a lot more of those technologies go in. Next slide, please. And when we want to talk about, you know, why we do energy efficiency, you know, we've kind of had that least cost resource on the left side there. Really what that boils down to is that it's a lot cheaper to save a watt than it is to generate a new watt. And we're an all requirements purchaser of Bonneville Power Administration, so we get all of our power out of the Columbia River Federal Hydro System. That has fixed capacity. There aren't going to be any new dams going in, and it's incumbent on us to try to find ways to serve really the same, you know, using the same amount of generation that we've got, be able to serve more consumers with that generation. Next slide, please. So looking forward, you know, we're you know, relatively small cooperative on the scale of things. But we also, like I said earlier, are responsive to our members, and we have to be able to kind of be that energy expert for them when they call in. So some of the things that we're looking forward to in the future is we're looking at getting into the battery energy storage space, looking at primarily, first and foremost, you know, piloting a utility scale battery that would be attached to one of our substations. But we believe that through what we learn in, using that battery, that we'll be able to help with our large commercial consumers on, consumer scale, and then also possibly, being able to help residential consumers that may have a solar installation and are looking at putting a battery in. Of course, any batteries that we have out on our line, we would like to be able to have, control over, and there's possibilities for new rate designs that are related to that. Secondly, the electric vehicle market is growing. We expect that it's going to come into our area in larger numbers very soon. So we, as a cooperative, we want to get out ahead of that. We have a subcommittee on our board that is looking at electric vehicles and future technologies. And one of the things that we really want to get into is into this managed storage idea, and what can we do, or managed charging, I should say, and how can we take control of this charging to benefit both the consumer and the cooperative. And then also, looking at using electric vehicles as a resource. So basically, these are batteries on wheels, and how can we use them as a dispatchable resource in the future? Next slide. So, one of the questions that everybody's asking themselves is this, a good time to get into battery storage? The technology has come a long way in the past decade. This is, due in large part to the, the motor vehicle sector, and you can give a lot of credit to Tesla for pushing the envelope on that battery density and creating batteries that are more cost effective. On the utilities scale size, we've seen battery storage come down in price enough that these just on even back of the envelope calculations, they are penciling out to be something that is cost effective enough to do a pilot on. And then of course, in reality, it's already happening. And one of the great things is, since it is already happening, it offers a utility the size of Missoula Electric to take advantage and learn from those who went first. Next slide. So what we're looking for is using battery energy storage as a peak shaving measure. So we'd like to be able to, clip off the top of those peaks on our peak days.
Hey,
we
Dan?
budgeted for 2021. Yes.
Sorry, if you could just wrap it up in maybe a minute or so.
Okay. Yep.
Thanks.
We budgeted $2021 to purchase a 100 to 200 kW battery for our distribution system, and we calculated a payback of around 9 years, which is really why we're getting into that. Last slide. And really, in the electric vehicle space, we know they're coming. We know that 90% of the charging is going to take place at home. This is a great new load that's coming our way, but we also have to be aware that we need to manage this charging, and then hopefully be able to take advantage of the great resource that it may be, as being able to take energy from that battery on wheels and put it back into our system. That's what I've got, Kyla. Great.
So it looked like we had a couple questions and a few questions from Diego on MDU's demand response programs, but it looks like Darcy was able to answer those. And then let's see. Trying to find that other question that came in.
I've got it here, Kyla.
Okay, thanks.
The question was, to what extent is Northwestern Energy's peak needs met by natural gas versus electricity? In other words, are winter peaks more of a concern on the natural gas side of the business, where renewables can't contribute as much right now, or the electricity side where renewables can contribute? So Brandy or John, would you be willing to take a swing at that one?
Yeah, I'll go ahead and jump in here. It's really close right now. It's 50-50 the summer peak, as I understand it. Again, I'm on the distribution side, so I don't have day-to-day knowledge on the supply, but our summer peak's starting to grow. Our winter peak, though, is still there. So, quite a few years ago, we had a higher winter peak. Now the summer peak is pretty close with winter peak. And so, where is our concern? The renewables, again, it's intermittent. Yes, it can help align with summer peaks because it's usually when the sun's shining and it's super hot out, and that's when we hit it. The winter peak is a struggle, though, because the sun's usually not shining and there's no wind. And so that peak is kind of, it's actually, it's both, it's natural gas, it's open market purchases. We have to go secure that, and sometimes that peak comes with a high cost to our customers. So I think that addresses your question, but feel free to.
Oh, John, I think you are paused.
I got cut off. My interconnection went unstable. Did you get all of that, or do I need to restate that?
We got most of that, just the last part of if folks want to follow up and get in touch with you.
Yeah, feel free to type a question if I didn't quite fully answer it.
Great. Okay, well, I want to leave time for our last panel, so we'll try to follow up with answers to any other questions that come in on this topic, but I'll hand it over to Ben Brower. Ben?
Great, thanks, Kyla. I'm going to wrap us up here with a spotlight on the Cabin Creek Solar Project. We have a few presenters with us today to talk through this project. In July of this year, Clenera and Basin Electric Power Co-op announced a deal to build two 75 megawatt solar farms near Baker in eastern Montana. Basin Electric's a generation and transmission co-op serving many smaller co-ops with power and transmission services across 9 states, including parts of Montana. And Clenera is an Idaho-based clean energy developer with 1,800 megawatts of solar in operation or construction across the country. I think what jumped out about this project was a couple of things. First off, at that scale, it's significant by Montana standards. The largest utility scale solar projects we have on the ground right now are just in the 2 to 3 megawatt scale. The other notable piece about this project is that when it's built, will be the first utility scale solar project built in Montana to serve Montana rural electric co-op customers. So wanted to give a chance for the partners in this project to share a little bit more of the detail of what they have in the works. So to kick us off, we have Andy Buntrock, Basin's Director of Strategic Planning and Communications, and Joan Dietz, Basin's Communications Manager. Andy, Joan, go ahead.
Hello. Andy and I will share some information on our involvement in the Cabin Creek project, where we'll be purchasing the output of that project. But to just give a little background of Basin Electric, if you'd go to the first slide, please. We'll talk about Basin itself. It's a generation transmission cooperative that was incorporated in 1961. We have 140 cooperatives, 18 of which are in Montana. And we serve a 9-state region that stretches from the Canadian border to the Mexican border. So in that area, we serve about 3 million customers and use a variety of resources to get them their power. We use about 2,500 plus miles of transmission to deliver that electricity. And something of note, in 2011, we brought online the nation's largest wind project owned by a cooperative in South Dakota. So we've been doing renewables for quite some time. And if you go to the next slide, Andy will talk a little bit about how our portfolio has evolved.
Thanks, Joan. Andy Buntrock here with Basin Electric Power. Can you hear me okay, Ben?
Yep, coming through loud and clear.
All right, sounds good. As Joan had said, we're a cooperative based out of Bismarck, North Dakota. We've got 18 members that are there in Montana. And it's interesting that, installing renewables is really nothing new to Basin Electric. We've been doing it for quite a long time. This particular slide kind of shows you a snapshot of where our capability has been all the way back to 2000 and then fast forward to just last year in 2019. And one thing about Basin Electric is that we're very unique in that we've grown about 50% in the last decade. And we've been able to meet that growth, about 80% of that growth, with renewables, natural gas, and market purchases. So that gives you kind of a taste to see where projects like this solar piece, this 150 megawatts here at Cabin Creek, is going to fit in well. Next slide, please, Ben. This is just a generation map. The darkened gray is our membership footprint. As we said, it stretches over about 9 states. And then you can also see kind of where all of our generators are located. And so you can see we have a very nice diverse mix of generation throughout our footprint of our members. Next slide, please. And this is a slide on the left. You can see our 2019 capability that you had seen earlier. But what this slide kind of demonstrates a little bit is that we're required by the energy markets to basically ensure that we can supply capacity. And so this is just a sample of the SPP regional trade organization, the RTO, and basically the allotted capacity that we're given depending on the type of generation unit. And so this kind of shows you how we're able to kind of intermix some of these different generation types into our portfolio. Next slide, please. Now I'll kick it over to Joan to kind of talk to you about where we've been.
And so you can see from this slide, the renewables have grown significantly from 2000 to 2019, going from 11% to almost 26%. And alone in this year, in 2020, we've signed not only the Cabin Creek project, but we also have Wild Springs and West River projects in South Dakota that will bring us some additional solar power. And then in North Dakota, the Northern Divide Wind Project is another project that we will be purchasing the power from on a renewable level. So that renewable number continues to grow as our portfolio grows and our loads grow to meet what our members need.
Thanks, Joan. And I'll just kind of wrap it up here. You know, we appreciate the opportunity to tell the Basin Electric story. You know, we believe in an all the above energy strategy that mixes in a good mix of generators. And this allows us to take advantage of the affordability of the renewables, yet, you know, maintain that importance of the reliability from some of our other generating units. So I will kick it over now to Clenera to discuss more of the technological aspects of this project.
Great. Thank you, Joan. Thanks, Andy. So for Clenera, we've got Jared McKee and Tom Fitzgerald. Jared is the Vice President of Business Development with over a decade of experience in supply chain consulting, program management. And since Jared joined the team, Clenera has contracted power purchase agreements on 520 megawatts of projects and has developed a pipeline of over 10,000 megawatts. Tom is the Director of Development. He's been developing utility scale solar projects across WEC for 11 years, overseeing the development, implementation, and disposition of more than 500 megawatts of operating projects and greenfielded more than 33 gigawatts across 8 states. I've asked these guys, they don't have any slides, but just to give us an overview of the project, the timeline for construction, and how it's coming together. Jared, Tom, take it away. Jared, you're still muted there.
All right, you should be able to hear me now.
Yep.
All right, fantastic. So we are grateful to be here, and we're excited to talk with the fine folks here in Montana about our Cabin Creek project. A little background on Clenera is really Clenera has been developing and working on solar projects for the past really about 6-7 years. And where we have seen most of our previous historical projects being developed has really been in the desert Southwest, kind of some of the areas where you would historically expect to see solar projects. As you have seen, the advancement of solar as costs have declined and efficiencies have increased, we have definitely expanded our footprint to where you now see our solar projects being developed in the Midwest, in the Southeast, in the Mountain West. We have projects in Idaho and Utah and Montana, several operating projects in Idaho and Utah, and then several development projects in the state of Montana. But it's really quite exciting to be discussing the advances of solar as far as market locations, because this has really been due to the efficiencies and the economics of solar, combined with the renewable nature, allowing a utility to have really a combined approach, as Joan talked about, is really looking at this combined approach where they can sprinkling in and getting a higher penetration of renewables and doing it at a cost that really makes sense for both them and the ratepayers. So with that, as far as a little bit of background from Clenera, I'll go into some more information on the actual Cabin Creek project itself. Clenera has been developing the project for the last year and a half. We engaged with Basin Electric due to their RFP back in, I think it was in 2018 is when they had held their RFP for additional capacity within the SPP market. The Cabin Creek project is 150 megawatts. It's located on approximately 1,100 acres northeast of the town of Baker. We have been really working through the development of this project for quite a while, and we're excited to move forward with a willing counterparty and have had that process going for quite a while as far as the development of both the project physically itself and also our coordination with Basin Electric on the project. We are interconnecting to an adjacent 230 kV line that's going right next to the project. We are in the midst of really getting through the SPP process as far as interconnection. That process, it can be both a challenging and rewarding process as far as getting through with SPP. We are currently just going through that process right now, and the project is expected to be online by the end of 2023. It's expected that construction will take anywhere between 12 to 16 months. Just depending on a couple of different inputs as far as timeline into our schedule. And so when we look at this project, we think it'll be an extremely valuable resource for Basin Electric, and will be something that they will be able to get clean and affordable economic energy and capacity over the next 15 to 25 years. Tom, is there any other updates or any other project highlights that you would like to add to the Cabin Creek project?
No, I think that was a great summary, Jared. Thank you.
Great. Well, thanks, Jared. So if folks have questions, feel free to type them into either the question and answer box or the chat box. Either one of those will work out just fine. I've got a couple for you guys just to kick us off here.
Sure.
I guess for Basin, in previous discussions of this working group, the generation and transmission working group, we've taken a hard look at the role energy markets play in resource procurement decisions. So I'm curious for you folks as a co-op that's serving and operating within multiple wholesale markets, how has that position affected the type of resources that Basin sees as serving your customers best?
Ben, this is Andy with Basin Electric. I can take this one. Yeah, it's very evident that the role of the RTO definitely plays a piece in what we're able to as far as our development of generators to meet load. You know, the beauty of an RTO is that it ensures that there is, you know, that everything settles correctly and that, you know, you pick up all those efficiencies. And I think we've definitely seen that through the SPP. I think Basin Electric joined SPP in about 2015, and we've seen tremendous growth in the renewables within the SPP footprint. I think that growth continues.
Got a question from Jeff Fox. Jeff's wondering, or first off, commenting, Montana is extremely lucky to have attracted the Cabin Creek Solar Project. His question, was Montana's energy tax environment deemed attractive and stable in choosing to develop the project here? And is Cabin Creek sensitive to potential tax increases?
That's actually a great question. There are definitely some unique items as far as Montana state tax. There was an attractive new and emergent tax structure that we did pursue on this project. That was very, very helpful for the project to achieve the economics that Basin Electric was looking for. The county was really a joy to work with. We were able to have a very cooperative and collaborative working session with the county as far as looking to get the project to a point where it was going to be of interest to Basin Electric. When you look at these renewable projects, it really is, you're looking at a lot of different inputs. And in order for us to actually project out a output, which is the price that Basin Electric would be expecting on a PPA rate, we go through and we do have to have stability on taxes and operating costs and CapEx costs. And so having some stability on the tax, specifically the property taxes within the state of Montana, was very, very helpful, as well as the folks from Fallon County.
Thanks, Jared. Another question from one of our attendees. How many construction and long-term maintenance jobs will be created by this project?
Yeah, so with 150 megawatts, the construction jobs vary just a little bit depending on how long of construction will be. But we typically see for this size of a project, I tend to do it in more construction years. If you have a construction job that takes 2 years, if you have 100 people that are working on it, to me, that would be 200 construction years. So typically what we'll see is anywhere between 350 to 400 job years on this type of a project. And then as far as the long-term maintenance, what you would see is anywhere from really 2 to 4 as far as long-term employees or full-time employees. And those will be kind of a varying level of employee depending on what you're doing from a vegetation management standpoint, as well as a operations and maintenance standpoint.
Thanks, Jared. Another question for you guys. Most of the recent large-scale generation we've seen developed in Montana has been wind. And I'm curious from your perspective, I guess, Jared or Joan, Andy, what's the value that solar built in Montana provides to utilities, and where do you see the biggest opportunity for solar development specifically in Montana? This will probably be our last question. We'll wrap up just in a couple minutes.
Maybe I'll answer that, my portion of that question, but Basin might be even better to respond to that. But one of the differences between wind and solar is they have different profiles. And so when you look at, especially when you look at specific wind projects, you can actually combine a solar and a wind project if you are a utility to have, you take these intermittent resources and you can look at their forecasted probabilities of what the profile is going to look like. And you may have a wind facility that typically blows at night and a solar facility that typically, it's producing during the day when the sun is out. And you can combine those together and really put together a schedule that matches your load profile very well. Whereas if you're just looking at one or the other individually, they may not match. And so when you look at solar, it does have a generation profile that typically matches the load profile of a utility with greater precision than you might find from a wind project.
Thanks, Jared. Andy, Joan, would either of you care to chime in briefly on that question?
Sure. I just probably echo what Clinera said there as far as the profile. They match nicely. Currently we have over about 2,100 megawatts of renewable power, and a large chunk of that is wind. And so that's why, as Joan mentioned in the beginning of our presentation, we're starting to integrate additional solar into this to basically take advantage of what he had just mentioned there as far as that differential in the profile.
Great. Thank you, Andy. Thanks, Jared, Tom, Joan, as well for joining us on this panel and giving us a little insight into the project you have in the works. Best of luck in getting it put together and in the ground. And with that, we're going to wrap up this session of the Montana Generation and Transmission Working Group. Thank you to all of our presenters today and our attendees. Thank you for the questions. And feel free to follow up with us. As I mentioned at the outset, we're planning to post a recording of this webinar at our website listed there on the last slide. Thank you all. Have a great Monday.